Okay, so good afternoon, everyone. So my name is Saprava. I'm the session chair for this. And in this session, there are two exciting talks. The first one is by Vishwa. We'll be talking to us about EFX for three types of agents. Thank you.
No, I think you have to long press or something. Long press Oh, अच्छा. Yeah. Hello.
Is it? Yeah, now it is. Yeah, I think it is.
I have already pressed it.
Yeah. So, what's a fair allocation instance? We have n agents and n goods, indivisible goods, and we're considering the setup where each agent values a given good at some value. So, in the general setup, the valuation is defined over subsets, but for this talk, we are only going to concerned about additive valuation, where value of a set is simply value of sum of every item in that set. So yes, V of S is simply sum of V of every item in that set. And an allocation is a partition of these items into what we call as bundles. So here, I mean, every item is allocated to somebody and exactly one person. For example, everyone's bundle consists of this monitor and this phone and cycle. So we have n bundles for every agent, like each agent. So that's a fair allocation. So very natural notion of fairness is called as the envy-free allocation, where Vi of Xi is more than Vi of Xj. That is, for any pair of agents I and J, I thinks his own bundle, his or her own bundle is better than anyone else's bundle. So this need not exist in general. A simple example is there are two agents and one valuable good. If you give it to two agents, one is going to envy, and if you give it to the other agent, this agent is going to envy. So EF does not exist. So an allocation is said to be EF if there is no envy in an allocation. So a notion that was introduced by Karayanis, Kurokava, Maulin, Prakash, Shah, and Van is any free up to any good. It's a very natural relaxation of any freeness where you say that envy is allowed to some extent. So that is, suppose there is some envy. We call this a weak envy if everyone of any good kills the envy. Like, so it's there is stress on any good. Like the envy should vanish as the minute I remove any single good from the agent's bundle. So here, so if the envy is not giving like vanished aftermole of good, we call it a strong enemy. And an EFX allocation should not have any strong enemy. That's by definition. And the weak enemy is allowed. So the question is, does instance EFX allocation? So this question has received a lot of like on the limelight for a while. So in the poll the questions, the authors commented that it's an enigmatic open question and highly non-trivial even for three agents. And in a magazine, Communications of the ECM, Arya Prakash mentioned that it's one of the fair divisions biggest problem, and there is a lot of uh, research going on in EFX allocations. So, okay, so what is known about EFX allocations? So, this is not the complete picture at all. I'm only limiting to complete allocations. Like there are various approximations of EFX. It's just limiting to complete allocations. EFX exists for two agents. That is just like two agents A1 and B1, and any number of groups EFX exists. And I'm also like some of these result are for more general valuation. I'm really concerned about additive for now. And it also exists for identical agents, that is any number of agents, as long as everybody has the same valuation function, say VA, then EFX allocation is known to exist. And Mahara showed that EFX allocation exists for two types of agents. That is like it's generalization from both the previous one, that is we can partition agents into a group A and group B, and everyone in group A think alike. Like they have the same valuation function VA and group B have the valuation function VB. So then EFX always exists. And EFX is also exists for three agents. This is a work by Chaudhary Garg and Melhon received the best paper and exemplary paper awards at C. So you have three agents A1, B1, C1. Any number of groups, EFX is known to exist. So what we show is EFX exists for three types of agents. That is, like we can partition the agents into group C, and each group can have any number of agents, and EFX can be EFX is guaranteed to exist for additive evaluations. So this generalizes the previous result what we known for EFX. So the setup is we have n agents, and n is a set of grids. We can partition the agents as A, B, C, and where A is all the agents who have valuation VA, and so on. So here is to it's a very common template in this area. We start with a trivially EFX allocation. So we give one item to any agent, like some starting point, and so this is trivially EFX. If any is removed the only item, then the enemy is vanished. So then what we do is, as long as there is some unallocated item G, so we have to we did the allocation in some manner, and we continue this process, and we want to show that this update, there is some progress in this update, and this progress eventually terminates. So this is the main idea. So we start with an empty allocation, a trivial allocation, and we want to complete the allocation by making some progress in every step. So how to measure this progress is the really important question here. So now I want to just give you a bunch of tools that we will be using, and probably also might find it interesting for research, in general for EFX. So the basic, the very bread and butter of this research is this AMD graph. So the set of agents are nodes of a graph, and if agent is agent B, then you just direct the edge from A to B. So here, for this allocation, this is the AMD graph. And we also assume another thing called the instance is non-degenerate. So what does it mean? So for any agent, if you give different sets of items, then the value that the agent assigns for each of this set is different. So this is an assumption that we can make because of the result by Chaudhary Malhan in 2020, that it suffices to show that EFX exists for under this assumption, then we can actually generalize it to, show it exists for any instance, in any degenerate instance. So, yeah, there's a small observation you can make here that for any allocation X, we need two identical events, like hooking collide, then if you think at least one of them is getting something, not getting M2 bundles, then it must be the case that one in this AI in this AJ or AJ in this AI. It cannot happen that both know each other or there is no any between each other. Is this clear? Like because we are assuming non-degeneracy crucially here. So yeah. So when we come to three types, just look at one type, the type A. When the MD graph is going to look something like this. We are assuming non-degeneracy, so there is going to be one agent who is purest of all, who is going to envy everybody in that group. Okay? So because of generality, we can assume that these bundles are sorted among these agents. So one is the purest bundle among all the agents. And it was the second purest and so on. So this is what the MD graph is going to look like. So for simplicity, I'm going to ignore these transitive edges. So I'm just going to represent it by this, like one single edge from AI to AI plus one. So the entire graph is going to look something like this, right? So you make a simple observation first. There are at most three sources. If an agent is not purest in his, he's going to be enveloped by the purest agent, so he cannot be a source. So the only set of agents is just the three purest agents. Okay, and another observation is if anybody in the group is suppose three elements B2, the purest agent also envelopes that person. The A3 envelopes B2 here, and since one is bigger, the A3 elements would also envelop B2. This is just simple observation that is at some point. So very common and very popular notion is this Pareto domination. And allocation is set to Pareto another allocation. If everybody is at least as happy in the new allocation, and one agent is strictly happier. Okay. So I hope you might have all seen this at some point. So a very easy, way to, it's a sanity check kind of, and one necessary argument is any cycle elimination. Suppose we give a graph, any graph, and if there is a cycle, that is A1, N is B1, C1, and C1, N is A1. Then what we can do is we can simply transfer these bundles, the entire bundles along these edges of this cycle, and everybody in the cycle gets here, and outside agent simply the edges to where that bundle goes to. And a generalization of this every cycle is this notion called champion. So this is something that some allocation. So you add an item G, say AJ, simply sit next to it and ask for all any this new bundle XJ union G. Okay, somebody is going to envy that because AJ herself envies that. We're assuming degeneracy, therefore no node is valued at 0. So every node is valuable. So AJ herself values this new bundle. Somebody envies to ask all these agents to envy the size of the smallest subset of this bundle that was still envy. Whoever reports the smallest subset, we call that agent the champion. Right? If there is any doubt on the champion, please let me know because this is very, yes. Yes. X, and you add a good G, right? And you ask who envies this bundle, the entire union bundle XJ union G, right? So there's this set of people who envy that. So each of them you ask, what is the smallest subset, smallest cardinality subset that you still envy? this subset of this union. Right? So whatever, like, he reports the smallest cardinality set. So you call him the champion of this agent, this bundle. Is that it? Yeah.
Several such agents.
Yeah, multiple champions. That is all. Yes. The cardinality to like, I mean, I think minimal will also work. Like, yeah, but minimum is also well defined, so it's okay. Yeah. So that subset we call it the minimally elite subset. Okay. Now this simple observation is that no one strongly envies the minimally elite subset because by definition it's a minimal subset. If you remove any item, it normally wants the smallest subset. It wants the smallest subset which was envied by somebody. So any smaller subset is envied by somebody. So it's not strongly envied by anybody. So it is a very it's a tool designed for EFX. Like, during EFX allocation, if there is a self champion, if J herself is the champion, then we can do a quick Pareto improvement that is replace this them with this minimally elite subset. So it is going to improve. And we know that minimally is the minimally elite subset. So this is a Pareto improvement concerning EFX. Is this okay? So this self champion can also be generalized. This is, so yeah, J is some isn't reachable from AI, like AMD edges, and AJ champions AI. Champions AI. This is not an enemy cycle because one of them is a champion edge, right? We can still do recycling in this. So along all this enemy edge, you are going to like pass the entire bundle, but along this champion edge, you are going to pass the minimum limit subset. So this is also another generalization of this any cycle elimination. Is it okay? Yeah. So a simple corollary is that the allocation if the graph has a single source, you can always do a Pareto improvement. Because every item to the single source, somebody is going to pay me. Because it is single source, everybody is reachable from it. So you can get this gadget and do this Pareto improvement. Okay? Yeah. So I mentioned that we start with some allocation and we have to do progress. So what are the usual progress measure and what is the progress measure that we use? Okay. So to show that EFX exists for two types of agents, we showed that for two types of agents, only partial EFX allocation. There is another EFX allocation which Pareto dominates this one. So Pareto domination is the progress measure for this result on two types. That is one possible progress measure. So we used progress measure called as the lexicographic domination. So like, so you sequence in the beginning of your algorithm that is agent 1, agent 2, agent 3. So you say that this an allocation dominates another allocation if this tuple lexicographically dominates the another tuple of the another allocation. So this is the measure for three agents. So what we do is we define slightly different progress measure. So it is the value. So you put in the beginning of the allocation, you pick one priority, like let's say group A. Okay, fix that group. And you say you just look at the value of the poorest agent in that group. That is, all agents in A, it's A, right? This is the progress measure that you will be using. Is it clear? Right. So note that this is compatible with Pareto domination. It's like suppose you start with an allocation, you have done a bunch of like 5 improvements, then you cannot do it anymore. So now if you do a Pareto improvement, you are not losing anything on your 5. Is that okay? Because the poorest agent is not going to be any poorer if you do a Pareto improvement. right? So for this progress measure, we generalize this champion cycle or energy cycle as follows. Like this is a we call it the five improving pseudo cycles. We call it something else. Thanks to Siddharth for suggesting this name. We call it now the pseudo cycles. So here, suppose A1 is some agent C3. Okay. Now C1 is some other. See, this is not any cycle. This reverse adjust from C3 to C3 to C1. If you squint your eyes and if you just, it's a cycle from among groups. There's an agent from group A, there's an agent from group C, there's an agent from group C, there's an agent from group, and so on. It's a cycle among these groups. So now there is one condition, we call it a cycle valid if both and it's indicating of P of one. So I mean, in this group, somebody else should not get this temperature. Okay, this constraint is there only for A1. We call this a pseudo cycle. Why? Because we can do a phi improvement here. Suppose these are the bundles of this agent. So what we're going to do is we're going to move this XA1 and B2, B2, B1. Okay. See that this XA1 is a bundle that is only in the previous stage B1. See XA1 will still be richer than B1. Suddenly will become the new polar station. It will go down for B2. He might be having a very good bundle. He's going to get a new bundle, but still better than B1. Similarly, this bundle is transferred to C3. It's a bundle that was enriched by C1. So C3 is not going to become worse than C1. And similarly, we can transfer this bundle to A1. See here, the point is that it is strictly improved. Okay, C3 might have decreased, not worse than the respective poorest agents. Right? So this is a fine improvement. So B2 and C3 might have decreased, but this is the order might change, you just resort. But the poorest agent still remains the same. Okay. So this is a fine improving cycle that we are going to do it. So this fine improving cycle, I defined it only for any edges, but similar to champion cycles, you can also define it for when one of the edges is a champion edge. Instead of moving the entire bundle, you just move the limit subset. Okay. And it can also be not just one champion edge, it can be multiple champion edge. But it just needs to be champion or different this champion. Okay. Right. So another important tool that we are going to use is the okay. Yeah, is resolving a strong, internal strongness. Suppose I consider a set of all the agents, consider some allocation x, which not necessarily is E of x. Now, suppose AI, all the strongly independent agents of AI lie within A. Okay. That is like, that is a set of all agents that AI strongly agrees and must be completely within AI. So what we can do is for each of these agents, we can replace the bundle by the minimally image subset of that into AI. It's not a champion, but what is not a subset, it is still enemies. You just forcefully replace the bundles of AL into AJ with this image subset so that this strong image is eliminated. Right? Now, these agents are still going to be richer than AI. Okay? So, we have eliminated every strong element of AI, and we know AI does not strongly limit anybody, and these agents are richer than AI. So, even these agents should not strongly limit anybody. Is that okay? Right. Yeah. So, it exists an application where all the strong enemies are contained within groups. There is no activist group strong enemies. Can safely eliminate this internal strong enemies and get an EFX allocation while limiting power 5. The first stage is 100 degrees. So we're really worried about strong enemies which go across groups. Is that okay? Yeah. So finally, this is the overview. So I won't be able to cover the proof. So we start with the partial effects allocation. I'll show you the case 3 of this proof. So cases, one is where the first agent is a source in this ML graph. And the case where it is not a source in this graph, it is separately. When it is a source, we have two cases where A1 is somebody from outside. That is, A1 is someone from B and C. And other cases when A1 is nobody from B and C. Okay, so A1 is a source, and we have the same set of cases where A1 is not a source. This is the structure of the proof. So in this talk, I'm going to present a sub-case of this last of this proof. Okay, and we're going to crucially assume that when A1 is a source and A1 is somebody from outside, we can somehow manage to deal with that. Okay, so in the case where the source and A1 is from B and C. In fact, I'm going to most restricted case in this subcase. That is, given a partial effects allocation such that A1 is the source and A1 G champions B1 and A1 is nobody from. So there are three assumptions. A1 is the source, A1 is nobody from B1 and C, and A1 G champions B1. So this is the case that we will see now. Yeah, I think I have got time. So consider the MD graph now. So we have all the tools to play with this. So G champions B1, right? When there is G champion, we know there is a MD subset. So we call that MD subset P and throw this B. Okay. And we forcefully allocate this T to B1. This is not an FX allocation because that is it's actually give okay. And now some FX allocation B1 is like strongly MD. That is okay, we will deal with it. So we want to give someone to B1, right? So we will define what's called as an outside set for B1. It's simply what is outside of its group. Okay. And we will ask B1 the best bundle from outside with respect to T, best bundle. So why, if you give that best bundle, so B1 initially had XB1, forcing it to keep this T. Now it chooses this new bundle, it might still not be better than XB1. It might still have gone down. If there is any strong enemy, it should be within this B because it shows the best from outside, it is not from outside. So if any strong is it should be contained within B and we can handle it. Right? We will ask B1 best bundle from outside. Suppose it picks something from A. So here again, there is a careful sequence of exchanges that we can do. This will give us a required fine improvement. So what happens is, suppose, what happens if B1 is somebody in C? Oh, sorry, yeah.
Oh, yes. So I think you've gone past. I just lost track of the fact that so X is a subset of XB1 union G.
Correct.
So you firstly give T to B1.
Correct.
G may not be contained in T.
G is contained in T.
Why?
That is an observation that also we can do. Like if previously the bundle was not being enriched, but suddenly after this having G, it is being champion. When champions of G must be present.
Okay, so the rest of XB1 B1 minus T is somewhere.
It's unallocated now.
It's unallocated.
Yeah.
Okay, so when now B1 starts to envy outside bundles, that XT1 B1 minus T is not part of that.
No, it is not part of that.
So this is why you're saying it could be actually of less value than the original XB1.
Originally you have XB1, now it's still SNP. It might be just small. It might not reach back to its XB1. Right?
Thanks.
So Like, trust me that when you choose something from A, you can somehow handle it. So what happens when something from C, let's say C2. So then we are going to ask C2. See, we are going to forcefully transfer this bundle of yours to B1. So pick a best bundle from the outside. Okay. Again, we pick when this bundle is from outside, we can any strong enemy induced will be contained within your own group and you can handle it. Suppose again pick something from you can see the sense of a cycle, but it's not obvious why this is a 5 improving cycle. But in this case, we can handle it. Like there is some sort of cycle from B to C and C back to A. It's not a 5 improving cycle yet, but this is again an easy case that we can do. Like the very interesting case is when we ask B1 to pick something from C, and we ask C to pick the best from outside, it picks B1. Something from B. So B1 picks from C, and C1 picks from B. That's just a typo. So nobody wants to pick from A. Okay. So what we are going to do now, how do we solve this? So the solution is a sub-potential function. Okay. So what is this sub-potential function? We're going to do something immediately, say, which seems counterintuitive. We are doing the allocation. We'll start now, we will undo it a little bit carefully. So we are going to remove some items from group C. That is, we carefully delete some of the items from C while maintaining EFX. Okay. So I'm not knowing how to carefully do that. So somehow we managed to delete some P from this group C and put it back to this unallocated group. The size of this unallocated set is now growing. That is our potential function. Because of phi is maintained. Like whatever the phi equal to A1 has the same matter. We're not touching that this deletion is happening from group C only. So now this cannot go on forever, this increasing size of unallocated. At some point, we must pick something from A because the agent in C is becoming poorer and poorer. Right? So now we just repeat it. And we are not touching the bundle C, so phi is maintained. At some point, C is slowly losing the goods. At some point, we will must pick from this A and we will be in a good case. Right? Yeah. So if you tell you the entire in this subcase, I did not tell you I like to say that you can carefully delete it. So you cannot carefully delete it. So what happens is you might again get stuck in this careful deletion. You want to increase this size of U, you want to delete and increase, but you might get in a situation where there is no deletion possible. So what's your solution? You will already see something that works. So we define what? Sub-potential function. So we call this the fake deletion. So what happens is, you don't actually delete an item, you pretend to delete that item. So I'm not formally defining it for the sake of, and I will lose everybody if I start going there. So you pretend to delete one item, C. Okay. So but there is a guarantee that this fake deletion happens at most once per every event in C. If an agent whose model is already with some fake deletion, and that is being picked by B again, that fake deletion will be realized into a real deletion. Okay? So there are actually 3 levels of potential functions. Okay? That is like, so we want to increase 5, but we get stuck. So we save that 5. Yes. Someone had a question? Yeah.
Yes. Was it to identify what is a valid deletion?
It is kind of that, but it's like so when we want the same bundle and deleting any item, nobody wants it.
Yes.
So we don't know if this is the exact bundle that we want to get deletion from. So we're going to say that assume that this is deleted and move on. So when you pick an item from outside now, from this fake deleted bundle, you're strongly in that. You're not still in that.
Yes.
So previously, if you pick the best bundle from outside, You don't have anybody.
Hmm.
You don't have any, which do not have any fake relation. You don't have these bundles which have some fake relation but are not strong. So that was the metric. They're like,
Okay, but later on, you sort of come back and identify an actual real deletion.
yes, and whatever item was deleted,
Yes.
then some agent, who's speaking that item is deleted. Like it's, the fake is that speaking up for him, so that item is deleted. He still pick that. So we're going to do that, and this fake deleted, we are going to put that to the pool. Right?
Thanks. Yeah.
So we have the increase 5, we will get stuck. So we will start unallocating, we get stuck again. So we do some fake deletion, but you have a guarantee that this fake deletion cannot happen forever. So at some point we will increase U, and that cannot go on forever. And then we are going to finally make this improvement. Yes. So again, this is the case 2. So I have not explained everything in this leaf. I have hid many things under the carpet. But if you are into this question, I encourage you to check out a paper. So the star here indicates that, so we are assuming that A1 G champions B1 here. So this leaf is that even if is nobody, what happens if it also doesn't champion B1? So that's a small case that we need to handle, but it's a chore to handle. You can do that, right? So now, here are some open questions that I care about is, so we have to be considering evaluation here, general evaluations. So some validity, or even a more general class of valuation called as a nice cancelable valuation. These 3 agents, which was initially proved by Chaudhary, Garg and Malhan, was later proved to exist even for the class of nice cancelable valuation by Akrami, Alon, Chaudhary, Garg and Malhan and Mehta. And so it exists. So, and what about general monitor valuations? It exists for 2 types of agents. Mahara is additive and then it exists for general. So we haven't touched anything beyond additive. So, it will be interesting to extend this to a more general class of valuation. So another open question is it really the number of unique valuation that makes the EFX problem hard? Like if you have some result that says EFX exists for some 17 agents, is it possible to prove that it's not the 17 agents, it's actually the number of unique valuations. You can have any number of agents as long as there are like 17 types of agents. Like whatever result that holds for K agents, does it hold for K types of agents? Like this would be a really interesting result to prove that the hardness of the problem, not in a computational sense, lies in the number of unique valuation, not the number of agents. Right? So another like obvious open question is what about 4 agents? That would be very good. Like, yeah. Thank you for your attention.
Time for a couple of quick questions. So Vishwa, can you remind us where you used additivity in your analysis?
Yes, we're not, in these cases, we are not using crucial
Things you describe don't use, but maybe the
other places we do use additivity. In fact, all this fake division stuff, it actually works for a general N agent. So if there is a champion edge, doing this first try to make something and then try to fake delete, you can convert the champion edge into a Hindu edge. But previously, after committing that in this case 3, I assumed that case is proved. If there is an NUH to outside, somehow I can handle it. But in a general case, I don't know how to use that NUH. Like, I think I have bored him.
No, there are no more questions. Let's thank the speaker again.
Okay. Hello, is this working?
Just put it up.
It's on. Yeah, it's on. How about now?
Yeah.
Yeah. It's in the desktop, somewhere. Okay. Yeah.
Okay, so our next speaker is Vignesh from University of Massachusetts Amherst. He'll be talking about fair allocation and simple valuations. Over to you.
Okay, thank you, Sopra, and thank you to the organizers, the local organizers. This has honestly been an incredible experience, and I've loved every minute of it. So this talk, in contrast to the previous talk, is hopefully going to be very simple, as in the title itself. And I encourage questions at any point. And yeah, so this is joint work with my advisor, Yared, a visitor, Zach, and an ex-postdoc, Cyrus. So, no? Also, I apologize in advance to a few people in the audience for what has happened. They did agree to letting me do this, but I may have taken it too far. It will become clear what I'm talking about in a little bit. So, the takeaway of this talk is very straightforward. In 2021, there's this amazing paper with Babayev, Ezra, and Fowler, which showed that you can compute Lexi-mean allocations when agents have binary submodular evaluations. I think that's a very small part of what they did. They also showed that you can compute Lorentz dominating allocations. These allocations have a lot of nice properties, and so on. What I'm going to show you here is our extension of this result, where we show that you can compute Lexi-mean allocations for a slight generalization of the valuation class. So instead of binary submodular evaluations, where each item is valued at either 0 or 1, we allow for like chores and like mixed mana in the setting. So you can have -1 for the chores, 0 for the indifferent items, and C for some positive constant C for the positive integer, C for the positive for the goods. If this slide doesn't make too much sense, that's okay. I'm just going to go into it. This is for the more experienced people in the audience. Yes. So this is a slide we've seen 4 times before now, where the difference is I know Photoshop. So we have a set of indivisible items, classic setting. I'm not calling it groups because the items might have negative valuations. And then we have a set of agents. Each agent has a valuation function. Now, an allocation now is a partition of the set of these items. In like classic fashion, I'm going to use VIFXI to denote the utility of agent I in this allocation. In this talk in general, and my interests in general are in the area of simple valuations, where each item is valued only like one of few numbers. For example, in this matrix here, each item is valued at say 0 and 1. And like in this here, it's like -1, 0, or 2. In general, it's a very small number. And the reason for this is there are a few reasons. The first one is these valuations are very easy to elicit. So even if like designers don't really know the fair allocation behind it, you can just ask to say, give me a list of the things you want, or give me a list of the things you don't want, and then whatever they're trying to do. The second reason is like there are many strong fairness objectives like natural welfare and so on, which suddenly become feasible to compute when you restrict the valuation class enough, which is really interesting and probably useful when designing mechanisms. And the final thing, and I think this is particularly interesting, is you can achieve multiple fairness objectives at the same time. I know Siddharth talked about how you can combine EF1 and for some additive valuations, but So you can do that, and also quite easily in polynomial time you can achieve these guarantees. So I think that's really interesting, and it's why we should look more into it. Now, just some basic definitions of evaluation classes here. People have talked about submodular evaluations today, yesterday, so I'm not going to go too deep into this. I just want to define the special class of binary submodular evaluations, where the key aspect is in the second point here, where the marginal gains of adding an atom is restricted to 0 and 1. So it's like very restricted in that sense. And, the generalization that I'm going to talk about, I'm going to call it -1, 0, C submodular evaluations. Here you can assume that C is an integer greater than 2 for technical reasons that I'll talk about later. And the main difference is that instead of the marginal gains being 0 or 1, now the marginal gains are -1, 0, or C. Now, this, in terms of extending 5 as a result. This feels like a natural first step because we're going from 2 valuations to 2 possible values to 3. And the second reason is it feels natural when you have a situation where you have goods and shows and you don't want to elicit too much. So you just want to ask questions like, what are the goods here? What are the shows here? What are like your capacity constraints or something like that? And this would be able to capture that class of valuations. Yes, and next up, fairness notions. I don't think this has been seen before, but this was very similar to Vishwa's progress function. We're going to look at the main fairness objective for this talk is going to be that of Leximin. Leximin allocation is simple. It tries to make the worst of agent as rich as possible. It tries to give them as much value as possible. Subject to that, you want to make the second worst of agent as happy as possible, and so on and so forth. Therefore, like you may have seen a few times today, is that when you have negative values, Nash welfare kind of becomes weirdly defined, because I don't yet fully understand what happens when you say when 2 agents have -1 each, you take their product and you suddenly get a positive number. So to make things simple, we're looking at some allocations. We also want to talk about a few other functions of fairness as well, like maximum share, MD freeness. This has been talked about already, so I'm not going to go into it too much. It's also not going to play a big part in our analysis. Now, the problem is this. When agents have -1, 0, C submodular valuations, there exists an efficient algorithm to compute Leximin allocations. And that's basically going to be the punchline of this talk. Now, to get that, I'm going to try to explain the proof as well as I can. Then it says like 0, 1 valuation because it is important. So we generalize in different ways, like instead of -1, 0, C, if you look at 0, 1, 2 as another possible generalization. Now, are there any questions so far? All right. Yeah. So, I'm going to start with the result from the Barman, Krishnamurthy, and Weiss from 2018, which is slightly different from this, but it's basically the same result, which is that there is an efficient algorithm which computes a Leximin allocation when agents have binary additive valuations. Now, this algorithm basically makes the following observation about the structure of the optimal allocation. Right? So say we have some allocation X here, and then we have the optimal allocation Y. Now, if you look at the allocation X, there are some agents, like say Vigna here, who has more items in our allocation than in the optimal allocation Y. We call such agents, say, richer agents. And then some agents like Rohit, who has fewer items than in the optimal allocation Y, we will call poorer agents. And what the result basically shows is that you can move from richer agents to poorer agents in a less structured manner. Yes, and you can do this greedily. For example, if you want to make Rohit richer, like give him more utility, you say he likes the items 1 and 2 in the optimal allocation, and we can give him the item 1, so which is now in Siddharth's bundle. And we could do this, but what we do is now, oops, sorry, Siddharth then become a better agent compared to the optimal allocation. So again, if you do that argument, Siddharth likes the bundle, item 3, which is in Meghna's bundle, and then we can do that. Essentially, we can keep doing this till we find a richer agent. Like now we've reached Meghna, so we can terminate this and just keep transferring goods along the path that we have found. And what this leads to is a different allocation x prime, which is better than x according to the Leximin objective. Right now, we move utility from Meghna with a lot of items to row which had a few items. So we have x prime, and x prime is more Leximin than x, or like has a higher egalitarian welfare, it's just more equal how we want to put it. This is the basic idea. And you can something like this, what I'm calling the local transfer property, that is, for allocations, if you have agent and a richer agent, you can move utility from some rich agent to some poor agent to kind of make the allocation more egalitarian. And in general, like this result is general, but what it says is that you can slightly mess up the allocations and make the utilities of agents more egalitarian until you finally get out of it more. Gives us the classical in that end. The algorithm is simple. So you start at a social welfare maximizing allocation, and then looking for these local transfers from rich agents to poor agents in a way that improves the Leximin objective. Right? So, for example, like if we have this here, where we find one. So from say Meghna to Rohit, we reach this intermediate allocation, and then we keep looking for another transfer. We can find another one, and then we finally terminate at this point where everyone has roughly equal utilities. If you just keep trying to equalize utilities till you can't anymore. And the local transfer property says that if you can't anymore, you're actually optimal. Because if you aren't at the optimal, there was some way where you could have used utilities from rich agents to poorer agents. Yes, so this is the basic tool here. This is a basic algorithm, and in 2021, sorry. Very similar algorithm. These improvements was drastically different. They showed that like this result generalizes to binary submodular functions as well. That is, like you can start at a social welfare maximizing allocation and then keep looking for local changes to improve the allocation. Now, what I'm not telling you is how they actually look for local changes, which is slightly more complicated. It's essentially the same algorithm. And the key result here is that the local transfer property, whatever I showed you, which held for the binary additive case, also holds for the binary submodular case, which is very useful if you want to like generalize, if you want to use this technique for more things. They also showed that like these allocations have approximate maximum share properties, or like EFX up to like some zero valued items, and so on. And this is the start of like where I try to build upon this, like trying to extend this result to new valuation classes and trying to improve this result in any way I could. And that leads us to -1, 0, C valuations. Now, again, just to repeat, what I'm going to tell you is just show you roughly an algorithm which can compute an efficient computer Leximin allocation in this setting. And the key approach is this. Yeah? Sorry, yeah.
So for goods, we know that Leximin will give us EFX.
Yes.
Does it say anything over here?
We can get that. I have a slide for that. Yes, but if I don't do anything, throw something at me. Yes. So now the key approach is this. Okay. Valuation function VI. For any bundle S, there has to be some number of items in S that give me a utility of C, some number of items in S that give me a utility of 0, and some that give me a utility of -1. This just follows from the fact that the marginal gains are constrained to -1, 0, or C. So what I'm going to do is I'm going to rewrite this valuation function by using alpha C sub I S to denote the number of items which give me a utility of C. Nothing too fancy. I'm just trying to isolate like how many items give me a utility of C here. And then alpha is 0 sub I to give me a utility of 0. And all the remaining items give me a utility of -1. Now, this is actually quite convenient, but the issue that this may not be easy to define. For example, if I have 3 items and the value of my bundle is 0, there are multiple ways that I can write this decomposition. For example, I could either all items give me a value of 0, or I can have like one item gives me a value of 2, and the remaining 2 items give me a value of -1. So, for this, or I'll work around for this, is to impose this additional assumption called order neutrality. And it's easy to understand, but a little hard to state. The idea is, like, say you have an agent and you have some bundle of goods as you do here, with some ordering of this bundle of goods. Say you have the orange, the grapes, and the bananas. The value for this bundle of goods can be decomposed into a set of marginal gains. That is, it is equal to the value of adding the orange to the empty bundle, plus the value of adding a grape to the bundle which already had the orange, plus the value of adding the banana to the bundle that already had the grapes and the orange. And we know this. These are the marginal gains, and we know that each of these marginal gains are constrained to be -1, 0, or C. Now, the assumption that I'm going to impose here is that this set of values, the 2 -1s and a 0, is independent of the order in which I add these elements to create these marginal gains. For example, if I had added the grapes first and then the orange, it would still like receiving marginal gains of 2 -1s and a 0. It might not have been in the same order, but it could have been like -1, 0, or 1. But the thing is that I will have 2 -1s and a 0. Now, with this well-defined set of marginal gains, I can now define alpha Ci and alpha 0I. This is straightforward. If I have 1, 0 in this list, alpha 0I, the number of items which give me a utility of 0 is 1. If I have like a multiple C values in this set, in this multi-set, the alpha Ci is essentially equal to that number. And that's the basic assumption we're going to make. I haven't told you that anything else like submodular functions satisfy this property, but what I'm going to tell you now is that if a -1, 0, C submodular function is order neutral, then we have 2 amazing properties. The first is that alpha Ci, the number of goods in my bundle, is a binary submodular function. And the second is alpha Ci plus alpha 0I, which is the number of items which are not chores in my bundle, is also a binary submodular function. Which means, like, I can plug in all the stuff from earlier about local transfers to kind of massage the allocation, which are lessened in allocation. Of course, it doesn't directly transfer with a few subtleties in there, but this is a basic idea, and if you just modify the proof slightly, it should hold. Yeah. Oh, we got that. Sorry again. I'm going to show you that all submodular functions satisfy the order neutral property. -1, 0, C submodular function satisfies the property. It means, so if I look at this set of marginal gains and I count the number of times C appears, the number of times a positive value appears, that function is a binary submodular function of the set of items. It's defined over the set of items. So, sorry, I should have made that clear.
So every S you define
Yeah, so
it can be when you add
Yeah. Yeah, it depends on the set S. So in this case, like alpha Ci is the number of items in S that gives me a utility of C. It's been more elaborately defined here as the number of given set, it's the number of times in this set of marginal gains that I receive a utility of C. Great question, thank you. Yeah. So yeah, it's basically yes. No, this doesn't mean C is more than two. In fact, like this kind of generally holds for submodular functions, submodular functions if you define the alpha functions appropriately. Yeah. So, where was I? Yes. So alpha C is a submodular, binary submodular function over the set of items O. And then alpha C plus alpha 0, which is a number of submodular function. And so, basically, we can now use the linear transfer property and use it to give us similar allocation. And the algorithm involves basic steps. It's not exactly like this, but I think for the sake of presentation, this should give us enough intuition. The first step is to find a lexicon allocation of the goods, which is basically the lexicon allocation assuming that all agents have valuation function alpha C, which is a binary submodular function. So based on all the stuff I talked about in the beginning, we can do this. And so assume this is our allocation. Step two is, now there are some items which have a utility 0 for everyone. Step two is as many of these items without allocating a chore. So the maximum number of items possible you want to allocate without giving everyone a negative utility. This is honestly the most non-trivial step because this could change the allocation in some sense. Like if we had item 1 here, you could have item 3 in this case and still after the step is done. But the idea is we still retain the same utilities, but we try to allocate items with utilities 0, so we allocate as few chores as possible. And the final step is again the situation where all the items remaining that we haven't allocated are chores to everyone. That is, like everyone values their minus 1, so we allocate them as greedily as possible. If so in this instance, Vignesh has a very high utility, allocate chores to her so that the stop agent is still as happy as possible. That's the algorithm. And yes, at this point, I'm aware that the pictures have gone too far. I apologize. But I hope it helped your understanding. So, now, this is that question. What functions are neutral? And what we show is that when C is greater than or equal to 2, minus 1, 0, C submodular functions are ordered neutral. And the proof is straightforward. I'm giving you a basic example here to illustrate it. Say you have a bundle of 2 items. This bundle can have the 6 possible values. It can be minus 2, minus 1, 0, C minus 1, C 2, C. And you can verify this. But if you look at any value, then C is greater than or equal to 2. There's a unique set of marginal gains that realize this value. For example, if my bundle is value minus 1, the marginal gains have to be minus 1 and 0 for the 2 items. And with this, you can show that the set of marginal gains is unique for the set of marginal gains is well defined, and these functions are order neutral. So it wouldn't matter if I did A2 first or A1 first, I would still get the same set of marginal gains. Of course, this is for items. To generalize this, a little bit of work is required, but this is the basic idea. Now, that's the C greater than or equal to 2 case. The C case is really interesting because we were able to show that maximizing egalitarian welfare is anti-hard when C is equal to 1. We can also show that when C is equal to 1, the function is no longer order neutral, but that's not as interesting. But this separation when C is equal to 1 and C is greater than 2 was quite surprising to me when I first saw it. It's Interesting to know is that if the variations are order neutral and C is equal to 1, the algorithm will still work. Yes.
And not just for submodular only or editor as well?
It is submodular. For additive, this problem, for additive, all additive functions are order neutral because the set of like, marginal gains are very well defined. Like you will know exactly how much marginal gain you can get. Yeah. And now for everyone's question, what other properties do these allocations have? The first thing we found is that these allocations are Lorentz dominating, which is not very surprising given the algorithm we used to get it. It's very similar to Fiverr's algorithm, and we can, yeah, we basically use that. What's interesting is when agents have additive valuations, like these allocations are EF1 and satisfy every, like give each agent their MMS share. But when they're submodular, they're not guaranteed to be EF1. And we don't know reasonable MMS guarantee here, but what I mean by that is there are instances where an agent receives utility 0, where MMS share is positive. So maybe it's like 0 MMS, but just see better. Yeah. And that's the algorithm. Are there any questions about the algorithm? Yeah. So, it's a little bit complicated. Maximizes utilitarian social welfare. And if you take the least valued K agents, and look at their total welfare, it's higher than least valued K agents welfare of any other allocation. So it's much stronger than Leximin. And it comes with a whole host of other properties like majorization related stuff, which not worth going into. Now, generalizing beyond this, sorry? I don't think this algorithm is truthful because it's something with the chores that if like you can pretend you don't have any chores and it'll allocate them to someone else because it tries to maximize the amount of items which are valued at 0. So there's some people who I don't believe it is strategy proof. So this is the last slide. Like -1 seems like an awfully specific to generalize this result. A more natural generalization arguably would have been say 0, 1, 2 valuations to increase the valuation, like increase the complexity in the all good setting. But it turns out that this problem is 80x hard for 0, 1, 2, even additive valuations. More generally, like with A, B, and C, if you have any 3 values, A, B, and C, which are not equal, computing a Leximin auto-match Nash welfare allocation is 80x hard, which is unfortunate. So I don't these techniques might immediately generalize for the max fairness guarantees we got in the binary case or the -1, 0, C case. Yeah. And finally, this is my last slide. The basic conclusion is that the local exchange properties of methods allow for the design of very cool algorithm. You should check them out. Nice. I think we're done. It's yeah. And as an open question, I think it would be interesting to see even if we want to it's hard if we can use these arguments for approximate algorithms. I haven't yet figured out whether it's possible. It seems likely, but I don't know. So, thank you very much.
We have a lot of time for questions.
Yeah.
So there are, you have 2 separate parts to this, right? You prove that it's order neutral and then you apply this algorithm. So if there are other classes of submodular functions which are, let's say, order neutral, can you extend your algorithm to such classes?
No, not exactly. We can show that, like, if an algorithm is order neutral, and if you have some threshold, say T, if some valuation functions order neutral, and you have some threshold T, you can say that the number of items which have utility at least two or provide marginal gain at least two is a macro rank function. But I haven't been able to use that more generally to come up with better algorithms, like approximate algorithms. I think that's definitely an interesting question. I've been successful there.
What is the meter then?
So if you have some submodular function which is order neutral, and you look at this function and count the number of items in any bundle which provides marginal gain at least p for any p, then this function is a macro rank function. So it seems possible that you could use these arguments generally, but I haven't been able to figure it out. The order neutrality property itself seems very interesting because it seems more general than I actually wrote this paper. That quite a few submodular functions seem to satisfy it.
Other questions? So I have a quick question here. So where are you using this property C is greater than 2?
For order neutrality.
So only for C greater than equal to 2, this particular submodular function will be.
Yes. It's
So essentially you will have this uniqueness.
exactly. This uniqueness only happens when C is greater than 2. You need C to be an integer for the analysis of the algorithm to work. When C is a fraction, it does not work. In fact, the problem becomes, again, it works hard for other values of C, which are not integers or half integers. So, yeah, so that's why you need an integer C, which is at least 2. Yeah.
This, if you have minus 1, 0, 3 halves,
Yes.
you multiplied everything by 2.
Yes. So that will give you minus 2, 0, C, which is honestly one of the open cases, which may not be, but if it's like minus 3, 0, C, I haven't looked at whether the algorithm fails, but we have a hardness result about this, like the problem of computer egalitarian welfare. It becomes hard. It mostly follows the proofs from negative valuations from Bhaskar, Murakami, and all those folks.
Okay, any other questions?
Yeah.
If not, let's go ahead.
Can you go back to the C equal to 1 case once, the NP hardness?
Yes.
You said minus 1, 0 C is order neutral.
Only when C is greater than or equal to 2.
If additive, you said,
Yes.
but you could introduce any number of minus ones and ones.
Okay.
So that's not order neutral, right? Even if additive.
Once.
Minus 0. But that is order neutral, right? Because the set of marginal gains that I get when, let's say I order a bundle in any one, start adding them one by one. The set of like marginal gains that I get are very well defined. They're equal to the value of each of the items that I add. So yeah, so that way we can define alpha C still and alpha 0. So this result would hold under additive valuations. And it has like a lot of really nice properties under additive valuations as well, but that's somewhat to be expected given prior work. Yeah.
Okay, so let's thank both the speakers of this session, and we'll reconvene at 4 o'clock again. Yeah, let's break for tea.
The last one, making it strong today.